In this short video, we're going to see how electrons are configured. Remember, electrons orbit the nucleus and they orbit in shells. And these shells are also divided in what we call subshells, which are the S shell, the P shell, or the D shell. And that is what we're going to look at. The lowest energy orbit is the closest to the nucleus, and that can contain up to 2 electrons. The next shell can contain up to 8. The third shell we think of as containing up to 8, and we do that when we're modelling the periodic table and ionic and covalent bonding. But for the subshell part of the topic, you need to know it actually contains up to 18 electrons, and that's the third shell. And the fourth shell, which is further away and has more energy, contains up to 32 electrons. Now, each shell is divided into subshells, and those subshells are divided into orbitals, and each orbital only contains 2 electrons, and their spin is in opposite directions so that they repel each other less, because electrons are both negative, so they will repel. So we've got 3 types of subshell. The first subshell is the S shell, and that only contains 2 electrons, so just one set of orbitals. The P subshell can contain up to 6 electrons, so has 3 pairs of electrons or 3 orbitals. The D shell can contain up to 10 electrons, so has 5 orbitals. So the first shell we know contains only 2 electrons, so we'll only have the subshell S orbital, and it's given the symbol 1s because it's the subshell S in the first shell. Our second shell around the nucleus can contain up to 8 electrons, and it's divided up into subshells. The 2s contains 2 electrons, and the 2p subshell contains up to 6 electrons, making 8 in all. The third shell around the nucleus can contain up to 18. So it's filled by, first of all, a subshell in the third shell, which is S, which has 2 electrons, the P subshell in the third shell containing 6, and the D subshell in the third shell containing 10, which make 18. So let's have a look at how we can work out the structure of the subshells. So these diagrams are really helpful. You do not get these in your exam, but you will have your periodic table. So I'll show you how to use that to help you build up these diagrams and also the numbers. So the subshells have different energy levels, and you can see 1s is the lowest energy, then you go to 2s, which is the second shell, and 2p, which is in the second shell. You then move to the third shell, where you've got the subshell S, and then you've got the P shell, the third P. Now, you'll notice there that the next energy, the next highest energy, is not in the rest of the third shell, but it's in the fourth shell, and it's the S subshell. So you have to fill up the fourth S subshell before you fill up the third D subshell. You've got to use the AFBAR principle in order to fill these up, and this is the principle. Electron fills shells, subshells and orbitals with the lowest energy first. Orbitals of the same energy must all be filled singularly before electrons of opposite spin are paired. When electrons are paired, they have opposite spins to reduce the repulsive effect. So I'm going to do a few with you so you get the idea. So the first I'm going to do is boron, which is here. Okay? And the easy way to work it out is looking at the periodic table. So boron has 1, 2, 3, 4, 5 electrons. So it's going to first have its subshell full on the first shell. So it's going to have electrons on the first shell full and we put them in opposite spin. It's then going to have the S shell of your second shell full, and then we fill up this and it's only got one more electron left, so that is it. Now we can write that as 1s2, 2s2 and 2p1. So let's do another example. This is sodium, which has 11 electrons. So I'm going to do it this way first. We've got 2 electrons, start filling up the next shell, 4, then we have to fill up the P's separately, 5, 6, 7, 8, 9, 10, 11. And you can see that sodium is here. So we've got the S shell full on the first shell, we've got the S shell full on the second shell, we've got the whole of the second P shell full, and then we've got the first of the third shell, S shell. So you can use the periodic table to easily write that 1s2, 2s2, 2p6 because all of the P shell is full, and then we've just got the 3p1. Now I want to also, before I move on, talk about ions, because sometimes you're asked to give the formula of a sodium ion. Now of course a sodium ion will lose its outer electron, have one electron less, so it won't have the 3p1, and it'll have the same structure as here because it's got one electron less, which is neon. So if you want to do a sodium ion, then its subshell configuration will be that, because it will be full. So that will be a sodium ion rather than a sodium atom. So be careful what they ask. Let's do one more, which is cadmium, and that's here. So you can see really clearly it's 2s first. So it's 1s, 1s2. It's then 2s2, 2p6. Then we've got 3s2. We've got 3p6. And notice now, because the first period in the transition metals is the D group, so this is a D group, so that's 3D, which means your 4s is filled up before your 3D. So we've got 4s2 and we've got 3d1. If you had to draw it, it's going to look like that. And remember, you're filling these up separately first and then putting the spin in there afterwards, filling those up, filling these up with the spin first. And I suggest in your drawing, when you're doing an exam, you do it like that so that you don't make a mistake with filling them up. I'll just do one more with you, which is aluminium. So aluminium, again, you've got 1s2 and you've got 2s2. You've got 2p6 with 6 electrons. You've got 3s2 because that's full, and then you've got 3p1. So quite often they just ask you to do that rather than show the orientation of the electrons in the orbitals. So if you had to do aluminium ion, remember aluminium's a metal, so it will lose 3 electrons. So it will lose those 3 electrons, so it will again have the same configuration as neon. So you'll just take off those outer electrons in the third shell, and so it will be 1s2, 2s2, 2p6. So I hope that's been helpful. The key thing is to use your periodic table and learn the fact that this is 3D, and then it's quite easy to work out the formations.